Welcome to lecture 3 of modeling and simulation of physical systems. It is about the state space description of the physical systems. In this lecture, we shall introduce to this new description of the physical system with the help of several examples. And in connection with that, we shall also describe the order of the system in terms of the number of energy storing elements. And then we shall describe methods to convert the differential equation representation to the state space representation, again with the help of several examples. Now, in order to understand the state space representation, let us consider an electrical circuit containing resistances and capacitances as shown here in the diagram. This electrical circuit is powered by the voltage source Vin. And here we ask a question that what is the minimum number of electrical quantities that we need to know so that this circuit is solved, assuming that the input voltage value, the resistances and the capacitances values are all known. Now, to answer this question, we first need to understand what do we mean by solving the circuit. So solving the circuit here means that we know the value of current and the voltage for each electrical component. So in this case, we have four electrical components, R1, R2, C1, and C2. So if the circuit is solved, that is, we know how much current is passing through this resistance R1. Therefore, we can also tell the voltage. Likewise, how much current is passing through the resistance R2, hence the voltage. Similarly, we need to know the voltage across capacitor C1 as well as the voltage across capacitor C2. Now we know that if we know the voltage across the capacitor, more specifically if we know the voltage waveform across the capacitor, then we can integrate that waveform to get the current. So here we are really asking what is the minimum number of electrical quantities, that is what is the least number of voltages and currents that we need to know so that we are able to solve this circuit. There can be multiple answers to this question, but one answer would be that if we know the voltage across capacitor C1 and the voltage across capacitor C2, then the problem is solved. And note that other possibilities also exist, such as the voltage across resistance R1 and the current through resistance R2. But let us go back to our main answer. To understand this answer, first consider that there are multiple ways to solve the circuit. For example, from your circuit theory course, you can readily tell that this circuit can be solved by first writing its differential equation because it has some capacitors. It is an example of a dynamic circuit. Therefore, it requires a differential equation. The order of the differential equation will be 2. And in order to solve the second order differential equation, you will need to know the initial values of the voltages across the capacitor C1 and the capacitor C2. And if you know the initial values of the voltages across the capacitor, then you can solve the differential equation and then you can tell the current and the voltage of each component of the circuit. The other way to think about it is to say, look, we can easily solve this circuit if we know the instantaneous value of the voltage across capacitor C1 and that across capacitor C2. If I know the instantaneous voltage values such as V2 here and V1, then the circuit is solved because I can easily calculate the current through R1. I can know the voltage will be Vin minus V1. Therefore, the current will be calculated easily. And also the voltage across the resistance R2, that is essentially V1 minus V2, hence the current. Similarly, if I know the voltage across the capacitor at time t, I can I can calculate the current through the capacitor by integrating the voltage waveform V1 for C1 and V2 for C2. So whatever method that we apply to solve this circuit, the end result would be that we need to know two quantities to solve the circuit. Now this first answer is one option. The other possibilities also exist, and you can convince yourself by doing an exercise that in any case we need to know two electrical quantities to solve the circuit. In this example, note also that there are two energy storing elements in the form of two capacitors C1 and C2. And we know that the capacitor stores energy in the form of electric field potential energy, often represented as proportional to the charge, which is again proportional to the electrical potential or the voltage. And we saw in the previous slide that we needed to know two electrical quantities to solve the circuit. And coincidentally, here we have two energy storing elements. Now this is not a coincidence as such. Later on we shall relate the number of energy storing elements with the amount of information that we need to solve the dynamic or the dynamical properties, or to obtain information about the dynamical properties of the system. By extending the ideas that we have developed so far, we can say that for an electrical circuit shown here containing three capacitors, requires three electrical quantities for a solution, and those can be the voltages across the capacitors, three of them. Again, you should remember that this is not a unique combination of the quantities that we need to know, and there are other possibilities that exist, but at minimum you need to know three electrical quantities, and that can be related to the fact that we have three energy storing elements in the system as three capacitors. This way we can actually generalize the idea of the solution requirement in terms of the number of electrical quantities that we need to know. For a circuit shown here containing n capacitors, then we need, if we have knowledge of the voltages across these capacitors at any given time, then we can solve the circuit. Also, the voltage across the capacitor at any time t requires the information about the initial conditions. Therefore, we can alternatively say that in order to solve this circuit, it is sufficient to know the n initial voltages across the capacitors. So this goes back to our very first observation in which we said that either we know the voltages across the capacitor at any time t, in which case we can just apply the KVL or KCL, or maybe just simple Ohm's law to find out the electrical quantities for the rest of the components. That is the resistances R1, R2, R3 to Rn. Or if we first develop the differential equation representation of this whole circuit and then try to solve the circuit, then we need to know the initial voltages across the capacitors, and we shall arrive at the same solution. Let us relate the initial condition with the dynamics of the system. For example, we know the capacitor stores energy in the form of electric field energy, and the inductor stores energy in the form of magnetic field. The storage reflects the ability to retain something, and in other words, the retention is linked with the presence of memory or memory element in the system. Therefore, in this sense, the initial condition indicates the presence of a memory element or some element that stores energy. In physical systems, we don't actually use the word memory element. We like to call them as energy storing elements. Memory element is often used in the context of computer architecture or computer engineering disciplines. Anyway, so with the introduction of dynamical behavior in the system, and system in our example is a circuit, what happens is that the output of the system has some kind of inertia, so that even if the input goes to zero, the output remains non-zero. So here is the output of a system, the circuit that we discussed last time. Input is a pulse of short duration. It lasts from time t naught, from time 0 to time t naught. The output gradually rises to achieve the amplitude that is close enough to the input till time t naught, and after that it begins to decay. But then it doesn't decay to zero instantaneously, rather the decay is gradual. And this blue shaded area is reflecting the ability to store, and hence the energy stored in the capacitor from time 0 to t naught is now being released after time t naught gradually. How many energy elements or energy storing elements do we have in the system dictate how complex are the dynamics of the system, and it is often reflected as the order of the system. But before that, let us take a step back and discuss complexity in a bit more detail. The complexity basically refers to the difficulty of solving a system for obtaining the profile of its dynamical quantities. For example, in case of electrical circuit, the complexity of solving the circuit will be the difficulty in obtaining the voltage and the current profile of all of its electrical components. In case of mechanical system, the complexity refers to the difficulty in obtaining the profile of displacement, velocity, and acceleration of all the components in the mechanical system. Now, how can we describe this difficulty in simple words or in mathematical formulation? Here we are going to say that more the number of energy storing elements, then accordingly we need more initial condition to solve the system. Therefore, the measure of complexity over here is the number of initial conditions required to completely solve the system for its dynamical quantities and to obtain the profile of its dynamical quantities that is time dependent. All right. So extending the idea of complexity to the order of the system, first note that system input-output relationship is described by the differential equation. And we have discussed, we know that the solution of differential equation requires the knowledge of initial condition. So if we have a system described by the nth order differential equation, then that refers to an nth order system, and that requires an initial conditions. So the order of the system, which is described in terms of the number of initial conditions required to solve the differential equation, and that describes the complexity in turn. However, one should note that the order of the dynamical system can never exceed the total number of energy storing elements from the system. In the previous example, we saw one-to-one correspondence with the number of initial conditions and the number of energy storing elements, and initial conditions are mapped to the order of the system. So in all previous examples, the number the order of the system was exactly equal to the number of energy storing elements. But later in this course, and I think that will be in the lab exercises, we shall see examples where the order can actually be less than the number of energy storing elements. Now let us discuss state space representation. It is an alternate to the differential equation formulation of the physical system. What happens is that a system described by an nth order differential equation, probably an n or a system of order n that is described using nth order differential equation, then state space representation essentially decomposes that one complex nth order differential equation into n first order differential equations. Now each one of those first order differential equation corresponds to an energy storing element, specifically describing the rate at which the energy is stored or transferred to other elements. So this is very interesting. We are now talking about the transfer or the transformation of energy. And we are trying to describe, or we are trying to decompose the complexity of solving the dynamics of the system in the form of the transfer of energy from one energy storing element to the others. The time dependent physical quantity that describes the rate of change of energy is called the state variable. So let us consider some examples of the state variable. In case of capacitor, the formula of the energy is half times capacitance times the voltage across the capacitor squared. Now if the capacitance is fixed, which is a realistic assumption, then the energy is dependent on the voltage across the capacitor. And we know that when the circuit is working or the circuit is operational, then this voltage can change, and hence the energy stored in the capacitor can change. So this voltage across the capacitor is an example of a state variable because it is describing how the energy is being transferred to the other components, or how the energy is stored in the capacitor from the other components. Kinetic energy, we're all familiar with, is half times mass times the velocity square in the mechanical systems. And here small v reflects the velocity. Higher the velocity, higher the kinetic energy. And the velocity is an example of a state variable because it dictates the kinetic energy of the system. Other examples of state variables: for instance, if we have an inductor in the electrical circuit, then the state variable will be the current, because the current dictates the energy in the inductor in the form of the magnetic field strength. The potential energy, such as that of the spring connected in a mechanical system, is half time the spring constant multiply the displacement from its mean position. So this displacement describes a state variable. Let us do an example of developing state space representation of an electrical system given in the form of an electrical circuit. It is the exact same circuit that we saw in the beginning, but how can we write down its state space representation is the problem. First of all, note that the input to the system is V in. That is the input. And the output, for example, is voltage across resistance R2, VR2 here. So we are interested in knowing the voltage across resistance R2. And because the circuit contains energy storing elements, therefore we can expect the behavior of the circuit as a dynamical behavior. Therefore, we are interested in developing the state space representation. The parameter values, the values of resistances and capacitances will be given as the input will be given. We know the output, and now the state space representation. Suppose we choose the state variables as the voltages across the capacitors Vc1 and Vc2. Then it is easy to see that we can write down the output as the difference of the state variables Vc1 minus Vc2. So that is part of the solution that is going to give us the state space representation. But the main part of the state space representation comes from writing the first order differential equation for each state variable Vc2 and Vc1. And you can use your electrical circuit knowledge to derive the two first order differential equation. So in case of equation number 1, we say that the current through the capacitor Vc2 is equal to C2 times the rate of change of its voltage. So on the left hand side, if you write down C2 times the rate of change of Vc2, then that's equal to the voltage difference across this resistance. So now note that the current through the capacitor C2 is the same as the current through this resistance R2. So what is the current through the resistance R2? That is essentially this voltage Vc1 minus Vc2 over R2. That is your right hand side. Now if you bring C2 from the left hand side over here, you will get equation 1. Likewise, you can write down a first order differential equation for equation number 2. And here again, we are saying that the current through the capacitor C1. So we are talking about the current through the capacitor C1. This current equals the current entering this node over here, that is current through R1 minus current through resistance R2. So the current through R1 is V in minus Vc1 over R1, and the current through R2 is Vc1 minus Vc2 over R2. And if you solve this equation, you will arrive at the form shown here. So take this as your homework exercise and verify that both equations are correct. So what we have learned is that in developing the state space representation for this circuit, we have 3 equations. And there are some properties that these equations fulfill. For example, equations 1 and 2 are expressing the rate of change of state variables as the weighted sum of state variables and the input. In equation 1 and 2, the left hand side is a rate of change of state variable. The right hand side is the weighted sum of the state variables and the input. So in equation 1, when we say weighted sum, what are the weights? The weights are the coefficients of the state variables. For example, the weight of state variable Vc1 in equation 1 is 1 over R2C2. And the weight of state variable Vc2 is minus 1 over R2 times C2. In equation 2, the weights of the state variable Vc1 is minus R1 plus R2 divided by R1 R2 C1. And the weight of state variable is 1 over R2 times C1. And the weight of the input is 1 over R1 C1. Which reminds me that in equation 1, the weight of V in is 0. So this is the rule that we are going to formalize in the next slides, in the next few slides, that the state space representation requires us to express the rate of change of state variables as the weighted sum of the state variables and the input. The other rule is obtained from the equation containing the output. So in this case, we have expressed the output as the weighted sum of the state variables, where the weight of state variable Vc1 is 1 and the weight of state variable Vc2 is -1. But just as we saw that in equation 1 and 2, the rate of change of state variables can also contain input in the weighted sum, it is also possible that the output is a weighted sum of not only the state variables but also the input. And for that, let us look at the same circuit, but this time we are interested in a slightly different output. We wish to obtain the voltage across resistance R1. That can be represented as V in minus Vc1. So if you write this down as a formal weighted sum, then you will say that this is minus Vc1. That is, the weight of the state variable Vc1 is -1. Vc2 is not in the equation, but we can say that the weight of Vc2 is 0 and the weight of V in is 1. Equation 1 and 2 are the same as before. So therefore, only the output has been changed. Therefore, there is no change in the first two equations because they do not contain the output variable such as VR1 or VR2. So now the output expression contains weighted sum containing input also. So from the previous example, we can generalize the rules of deriving the state space representation. The first rule says that the derivative of the state variable must be expressed as the weighted sum of the state variables and the inputs only. This only word is very important. You can't express the derivative of the state variable, which is essentially the rate of change of state variables, as something other than the weighted sum of state variables and the input. The other rule says that the output expression must be the weighted sum of the state variables and the inputs only. Once again, I would like to emphasize the only. Now, weighted sum cannot contain any derivative of the state variable or the input. So we've been saying that everything must be expressed in the form of weighted sum of state variables and the input. But then the input and the state variable must not appear in the form of derivative. For example, we cannot represent the derivative of the state variable Vc2 as the weighted sum containing the state variable Vc2 and the derivative of the input. So this is incorrect because we have derivative of the state variable. Sorry, this is the derivative of the state variable. So yeah, this is not allowed. Likewise, we cannot have the derivative of the input. That is also not permissible. Similarly, weighted sum must only be a linear sum. That is, this weighted sum cannot contain the nonlinear function of the state variables and the input. So for example, you cannot write the rate of change of the state variables as a weighted sum containing the square of a state variable such as Vc2 square. That's not allowed. Similarly, if you look at the output equation of the state space representation, the weighted sum must contain a linear function only. That is, no square root, no power, no logarithmic function is allowed. Therefore, this is also incorrect. These rules must be obeyed to be able to correctly obtain the state space representation of this physical system. We have seen that the state space representation is very similar to system of linear equations, with an exception that the left hand side may contain the derivatives of the state variables. And we know that the system of linear equation can be represented in the form of matrices. The only issue is that somehow we have to fix the derivative notation. And once the notation is fixed, then we can proceed with the matrix representation of the state space form of the physical systems. We are going to use the dot notation to represent the derivative. So let the rate of change of some state variable such as Vc1 is written as Vc1 and the dot on top of the state variable. So this Vc1 dot. Similarly, Vc2 dot represents the derivative of Vc2. And from here onward, we are going to represent the derivative in the form of this dot notation. So for any variable, might it be a state variable or the input variable, x dot means the rate of change of x. Then the previously developed state space equations can be represented as matrix vector multiplication form. So remember equation 1 and 2 of the previous example. These are shown in the first matrix vector multiplication as well as addition. So Vc1 dot, that is the rate of change of Vc1, is this coefficient multiplied by Vc1 plus 1 over R2C1 times Vc2 plus 1 over R1 C1 times Vn. So Vc2 dot will be 1 over R2 C2 times Vc1 minus 1 over R2 times Vc2 plus 0 times Vn. And the equation 3 in the matrix form is given as VR1. So this was the first example output where VR1 was essentially the second example where the output was the voltage across the resistance R1. That was V in 1. So the coefficient of V in 1, V in is 1 minus Vc1. So the coefficient is minus 1. So these matrices are containing the coefficient. The coefficient of Vc2 is 0. So one thing that we have learned from the matrix representation of the state space form is that we have some vectors containing the derivatives of the state variables and a vector that contains state variables without derivatives, and then a vector containing the output, and everything else is based upon the parameters of the system, which are comprising the coefficients in the form of the values of resistances and capacitances. So we now arrive at the canonical form of the state space representation, where the vector on the left hand side containing the derivative of the state variable is represented by capital X dot. This dot indicates that this vector contains the derivatives of the state variables times, so this x dot equals a times x plus b times u. So x is a vector containing state variables without derivative and x dot with derivative. A describes the characteristics of the systems, the values of resistances and capacitances in the form of coefficients. This becomes the weights of the state variables in the state space equations. B also contains these weights, but these weights are multiplied with the input. Similarly, the other equation containing the output has Y. So this matrix Y in this example contains only one element. It's a single output system. So y equals c times x plus d times u. So this c is a row vector, again describing the weights to be multiplied with the vector containing state variable, that is x. And d contains the weight matrix, which is to be multiplied with the input u. Now note that the matrices A, B, C, and D are made up of system parameters. And these system parameters are constants, that is the values of resistances and capacitances. These matrices are defining the systems. The other matrices are containing the variables, which are time dependent. Sometimes it is difficult to directly describe the state variables in the form of equations that we saw earlier. And in those cases, what we can do is that we can instead develop the differential equation of the system first, and then try to convert it into the state space representation. So going from differential equation to the state space representation, let us consider an example of a system whose input is u and the output is y. Again, these are time dependent quantities, so I've shown those with the help of parentheses containing the time variable t. So let us do an example containing a second order differential equation, a2 times y double dot plus a1 times y dot plus a naught y equals to bu. So remember, a2, a1, a naught, and b, they are coefficients and they are constants. What is going to be the state space representation of the system? We know the output of the system is y. We know the input is u. But what are the state variables? So in such cases, you have to define state variables by yourself. In this example, let us say we have state variables, two of them, x1 and x2. And the reason of choosing two state variables is because the order of the differential equation and the order of the system is 2. So with that, let us proceed and follow the procedure. So in the first step, we are going to say that let x1 equals to y. That is, our state variables has been set equal to the output y. What that means is that if I take a derivative of y, this gives me the derivative of x1. In other words, x1 dot equals y dot. With x1, our first state variable, now we wish to relate x1 dot with the other state variable, that is x2. And the rules say that x1 dot must be expressed as a linear sum of the other state variables or the input. So let us just set x2 equals to x1 dot. And this is a valid state space equation. Let's call this equation number 1. Now we proceed to represent x2 dot. So the second state space equation requires us to express x2 dot as a linear sum of the state variables and or the input. So x2 dot, we know that x2 dot will be equal to x1 double dot from here. If I take a derivative of x2, that becomes x2 dot. And if I put x2 dot here, that becomes x1 double dot. And x1 double dot is same as y double dot, as we saw in the previous slide. Now we wish to express x2 dot not in terms of y double dot, rather in the form of the linear sum of the state variables. And this is where we make use of the original differential equation. The original differential equation says that y double dot is equal to minus 1 over a2 y dot minus a naught over a2 y plus b over a2 times u. And y double dot is same as x2 dot. Therefore, x2 dot after simplification is represented as the linear sum of the state variables x1, x2 and the input. So this is the second state space equation. The third state space equation should relate output with the linear sum of the state variables and the input. And we know already that the output has been set equal to a state variable. So y is equal to x1 is the third equation. So now we have all the equations to express to completely describe the state space representation, and we can further represent that in the matrix form as shown here. So in the matrix forms we get the matrix A as containing 4 entries 0, 1, minus a naught over a2 and minus a1 over a2. The matrix B is a vector and it contains 0. Second entry is b over a2. C is 1, 0 and D is simply 0. D is simply 0 because the output expression contains a linear sum in which the weight of the input is 0. And as before, X simply contains the state variables in a column matrix or a vector x1 and x2, and x dot is also a column matrix containing x1 dot and x2 dot. Capital Y is just 1 by 1 matrix containing the output variable y. So this is a complete state space description of the example that we have just seen. The state space of an nth order system in case of single output, as was the case in our example, has 4 matrices. A is an n by n matrix. So the second order system, n was 2, so A was 2 by 2 matrix in the example. B is n by 1 matrix, it's a column matrix. C is a row matrix, 1 by n. And D is just scalar, essentially it's 1 by 1 matrix. For case of multiple outputs, suppose the system has multiple outputs, or we are interested in analyzing dynamic quantities represented as the outputs of the system. And suppose we are interested in simultaneously knowing the m outputs, m quantities in a physical system, then there is no change in the dimensions of matrix A and B. Only the matrices associated with the output will be changed. So from 1 to n, as in case of single output, the matrix C and D had both 1 row. In this case, with m outputs, matrix C and D will have m rows with no change in the number of corresponding columns. Now, all of this is true as long as you have an nth order system and it has single input. But what if we have multi-input system and multi-output system with multiple inputs and multiple outputs? Then we can still follow the state space description derivation that we have seen. And what we can do is that we can simply develop multiple state space representation, one for each input. So if we have a multi-input and multi-output system, then for each multi-output, you derive the state space representation for each input. So let's say you have k inputs. You develop k state space representations of this 4. Your homework exercise is to develop the state space representation of a third order system. In this case, you'll be using 3 state variables x1, x2, and x3. The state space example that we saw in the previous slide was relatively simple in a sense that the differential equation did not contain the derivative on the input on the right hand side. But very often in the formulation of the differential equation, it may be the case that the right hand side does contain the derivatives of the input. So let us now consider the same system with the modification that the right hand side of the differential equation is now containing the derivative of the input. It is in the form b naught u plus b1 times u dot. The left hand side is the same as before. The solution in this case will be to decompose this differential equation into a set of 2 somewhat simpler differential equations, and we are going to utilize an auxiliary variable w. So we are going to claim that it is possible to decompose this single complex differential equation into 2 differential equations as follows. The one of them is a2 times w double dot. So this auxiliary variable w has been introduced. So a2 times w double dot, a1 times w dot, a naught times w. The linear sum is equated to the input u. The other equation equates output with the linear sum of weighted linear sum of w and w dot. So b1 times w dot plus b naught times w. Now why is this claim true? Well, we saw in the last lecture about the representation, the transfer function representation, and the differential operator representation equivalence. So in order to prove that this differential equation is the same as the set of the 2 differential equations shown here, let us express equation 1 in the form of the derivative operator d. And we said last time that this derivative operator can somehow be treated just as a variable. So equation 1 can then be represented as a2 times the derivative operator capital D square plus a1 times capital D plus a naught. This whole thing applied to w. So essentially, when we say that this whole weighted sum of derivative operators is applied to w, then there is no difference to say between that and saying that this quantity inside the bracket is essentially multiplied with a w. So the application of the linear sum of the derivative operator on some variable w is the same as the multiplication of this quantity inside the bracket with the variable w. That is set equals to u. And then you can bring that whole quantity inside the bracket as the denominator on the right hand side. So that's w equals u over a2 times capital D square plus a1 times t plus a naught. Similarly, you can massage equation number 2 and express w as y over denominator containing b1's time capital D plus b naught. And so after equating equation 1 and 2, because they are both equal to w on the left hand side, you arrived at the expression. And this expression, if you convert this derivative operator back into the derivative, then this gives you the actual differential equation that we started with. So this proves that this equivalence is correct. That is, we can represent the actual differential equation as a set of two differential equations, 1 and 2. So once this decomposition is obtained, then the rest of the task is relatively straightforward. The auxiliary variable w is set equals to the state variable x1. So our state variables are again x1 and x2 as before, and hence the derivative of w equals derivative of x1. Now we wish to express the derivative of x1 in the form of the linear sum of the state variables, which are x2 and the input variable, that is u. So we need to let, once again, set x1 dot equals to x2, and this is our equation. Let's call this equation 3. Furthermore, we need to express x2 dot as a linear sum of the state variables and the input. But first note that x2 dot is actually equals to w double dot, because if you take a derivative of equation 3, you get x2 dot, which is x1 double dot, and then that becomes w double dot. So how can we so we now need to eliminate w, because this was a placeholder. It is just an auxiliary variable. It is not a state variable. So we need to eliminate w. So w can be eliminated from equation 1 and 2. So if we utilize equation 1, we can eliminate w, and we can express x2 dot as the linear sum of state variables x1, x2, and u. The weights of x2 minus 1 over 1 minus a1 over a2 of x1 are minus a0 over a2, and of u 1 over a2. The second equation, which was obtained by decomposing the original differential equation, that can be used to express y equals b1 times x2 plus b0 times x1. And this is easy to see because the equation 2 contain a coefficient multiplied by w and some other coefficient multiplied by w dot. And w is x1 and w dot is x1 dot, which is x2. So we have b1 x2 plus b0 x1. And therefore we now have a complete state space representation. The state variables x1 and x2, and the output has been taken as y, and the coefficient and the corresponding matrices are shown here. So with that, we proceed to your homework exercise, which is to develop the state space representation of, again, the second order differential equation describing the same system, but with the change that the right hand side now contains more derivatives of the input. In fact, we now have a term u double dot, so second derivative of the input is also appearing in the differential equation. Here a nice hint would be to utilize equation 1 alongside equation 2 in deriving the expression of y. So which is a bit different in a sense that here in this example we just use equation 2 and obtain the expression of y. In this example, however, you may need to utilize equation 1 and 2. Both of them may be used to express y for the correct state space representation. With that, I would like to formally conclude the lecture. I'm sure you enjoyed this lecture and you may have lots of questions For that, we are going to have our regular questions and answer sessions on Thursday afternoon. That will be starting at 2 p.m. So till then, stay safe and have a nice day. Thank you. Bye bye.